So assignment number 3, so as I mentioned last time, assignment number 3, we're going to have it due on Monday the 8th. Unfortunately, spring break is, is going to be in between now and then. Anyway, you're welcome to turn it in before spring break if it makes it easier for you, or after, whatever suits you better. Exam 1 will be on chapters 1, 2, and 3, and that's going to be on Wednesday, the 10th. Okay. Still working on section 3, or chapter 3. Are there any other... one other thing I wanted to mention. So yesterday I did a problem number 3. I did it as an example. I didn't mean to do it. So here's a new problem number 3 on this assignment here. So let A, B, and C be sets. Prove that A minus B union C is equal to A minus B minus C. By showing that, and what we were doing last time is that you can show two sets are equal, okay, by showing that the first set is a subset of the second set, and the second set is a subset of the first set. Okay, so that's a general method for showing two sets are equal. You don't have to do it that way. You can do this by those set identities, but you're going to do number 2 via set identities, De Morgan's law and stuff like that. De Morgan's law, distribution, commutativity, and identity, and those sorts of things. Here we want to show this more general method. Okay, so there's a new problem there, number 3. Okay, so that will be done as we've been doing these examples from last time. So last time we showed that 2 examples of that sort. Right. Use the method above to prove that A minus A intersection B is equal to A minus B. All right, and we did that by showing A minus A intersection B is a subset of A minus B. And the first sentence of such a proof is this. Let X be an element of the first set. Let X be an element of the first set. And then you argue logically to X is an element of the second set. Such a proof always looks like that. Why do we do that? Well, I mean, we're trying to show that this, containment statement is true. Implication is a containment statement, as we've been saying since the beginning of the semester. Essentially, if X is an element of P, then X is an element of Q. So, assume you've got an element of P, show it is then an element of Q. The only time an implication is false is when this is true and that's false. So, we just want to exclude that. Assume this is true, show that this has to be true. In other words, true that implies false doesn't happen, so the implication statement is true. And then the reverse containment. The second is a subset of the first. Let X be an element of the second set. Okay, and then show that X is an element of the first. And then we did this example. And then we'll do some more as time goes on. Now remember, showing one set is a subset of another is essentially showing that an implication statement is true. Where's that? Okay, so we have shown that two sets P and Q are equal by showing P is a subset of Q and subset of Q is a subset of P. All right, and both tasks involve showing that an implication statement is true. Remember, P is a subset of Q when X an element of P implies X an element of Q is always true for every X. So now, for general implications, okay, we've been using what's known as the direct method of proof. The direct method of proof to do those. Assume X is an element of P, show X is an element of Q. For general implications, and for this type of implication as well, there's also two other types of proof strategies. So for general implications, R implies S. To show this is true, there's three basic methods. Direct proof, assume R is true, show that S is then forced to be true. In other words, this true, this false doesn't happen. Okay, because that's the only time an implication is false. When the hypothesis is true, conclusion is false. Contrapositive. So direct proof, contrapositive proof. I'll just call it contrapositive. Assume S is false, show that R is then forced to be false. In other words, this being false makes this false. In other words, you don't get true then false. So this is essentially showing that the contrapositive statement, which is logically equivalent, is true via direct proof. So it's a direct proof in the other direction. Assume S naught is true. In other words, show S is false, show R is false. Contradiction. Assume R is true and S is false. That's the only time an implication is false. When the hypothesis is true and the conclusion is false. So assume that. Assume the negation of what you want to show. All right, and then find a contradiction, P and P naught. Since P and P naught cannot possibly be true, it must be that your initial assumption was wrong. Right, so the implication must be true. Right, we've all argued by contradiction, just sort of informally. For those of you who have had, small children, I'm sure at some point they asked you, or I'm sure maybe you don't remember, asked your parent or teacher or something, well, what's the biggest number there is? Is it 20? Is it 100? Is it 1,000? There has to be some biggest one. And what do you tell them? What were you told? Why isn't there a biggest number? Why isn't there a biggest number? Or is there a biggest number? We've just been fooling ourselves all along. Come on, guys. Assume B is the biggest number there is. All right, assume B is the biggest number there is. What's wrong with that? What's the contradiction? Hello? Assume B is the biggest number there is. Bazillion is the biggest number ever. Well, that's what we're trying to show, right? We want to show that there's infinitely many. There's infinitely many because there's no biggest one. Right? But we can't say that there's no biggest one because there's infinitely many. But you're hitting on it, the right idea. What's bigger than B? B is a number. What's bigger than B?
B plus 1.
Yeah. Oh, B plus 1 is a number, right? And B plus 1 is bigger than B, right? But B is the biggest. I mean, so that's the contradiction right there. B is, but B is the biggest. So B is the biggest, however, B is not the biggest. Right? So I guess that's what we're trying to say. So B is not the biggest. And B plus 1 is bigger than B, so B plus 1 is not the biggest. So the contradiction is B is the biggest and B is not the biggest. Well, it can't be. So your initial assumption must be wrong. Your initial assumption must be false. So that's the heart of a proof by contradiction. So let's do an example. Not contradiction, just an example of some if-then type proofs. Again, involving sets. All right. So prove the following statement is true. Maybe we'll do it all three ways. If A minus B union B is equal to A, then B is a subset of A, period. So we want to prove that this statement is true. Let's do two different proofs. Let's do two different types of proof. Okay. Here's a direct proof. The direct proof, assume the hypothesis is true. So what do we assume is true? What is the first sentence of my direct proof? Right, direct proof. We're trying to show that if R then S, or R implies S, is true. So assume R is true, show that S is true. So down here, what's my first sentence?
Let X be an element of A minus B union B.
We have to assume that the hypothesis is true. Here's the hypothesis.
Oh, okay.
This is not true in general, this equation right here. This set equation, A minus B union B, is not in general equal to A.
But we're assuming it is.
Assuming it is. Right, so that's your first sentence. Assume that A minus B union B is equal to A. Okay, so maybe before we get into that, let me just be clear about something. Note A minus B union B is not A in general. It's not always A. How can I verify that? What do I need to do? Well, I mean, horses are not brown in general. What do I need to do to display the truth of what I'm saying? Not all horses are brown in general, or horses are not brown in general. In general, like always. So maybe we'll say it that way instead of in general. Is not always equal to A. Right? Horses are not always brown. What do I need to do to verify that to you? I need to show you what?
A horse that isn't brown.
Yeah, the proverbial horse of a different color. Right? Here's a white horse. He's not brown. Do I have to show you more than one?
No.
No. I mean, it might be nice to, but not really, no. Okay, so, sorry, on my notes here. So here, I just need to give an example of two sets, A and B, where this is not always true in general, right? Essentially, when B is not a subset of A. So we'll say A is equal to 1, 2, 3. B is equal to 3, 4, 5, say. Right, so A minus B union B is equal to what? Well, A minus B is 1, 2, 4, 5. Union B, 3, 4, 5. Which is equal to 1, 2, 3, 4, 5. Right, which is not equal to A. So, for example, let A be equal to this and B be equal to that. Let me write it out a little bit more formally. Right. For example, let A be this, B be that, then A minus B union B is, well, A minus B is 1, 2, 4, 5. B is 3, 4, 5, taking the union of those, 1, 2, 3, 4, 5, which is not the same as A. It's bigger than A. All right? So here we're trying to prove this statement. If A minus B union B is equal to A, so, it might be, certainly could be. I mean, like if B is the empty set, that's certainly true, right? It could be that this is the case. So assuming this is the case, show that B is a subset of A. So assume that A minus B union B is equal to A. Now do what? Now I got to show that the conclusion is true. What's the conclusion in that implication statement there? I assume the hypothesis is true. Now I must show the conclusion is true, forced to be true.
Show that B is a subset of A.
Yeah, we want to show B is a subset of A. How do we do that? What do I start with to show that B is a subset of A?
Let X be an element of B.
Yes. Now let X be an element of B. We want to show that X is an element of A. So because X is in B, what set does it belong to? Does it belong to this? Does it belong to this set? What's the definition of union? Right? X union Y. Well, that means X union Y. P union Q is equal to what? It's the set of all X such that X is
That
bound.
X is in P and or X
Or.
is in Q.
All right. So X is in B. So is it in this?
Yes.
Yeah. Because it's whatever union B. Because X is in B, X is in B union whatever. All right. So X is in that B union whatever. Well, whatever union B. A minus B union B. Right? By the definition of union, let's say that. Although it's better not to say it, I will say it.
Which means that X is in A minus B or X is in B.
All right, but one need not go that far because we already know that set is equal to A. Right?
Oh, okay.
Right? By assumption, that set is equal to A.
Right.
So by definition of union, but yes, that could be a possible next step. Like if you're trying to prove other things, in general, that's kind of a good strategy to follow. What you were saying by the definition of union, X is in this, and because A minus B union B is equal to A, we must have that X is in A. Is that it? Is that what we needed to show? We were trying to show what?
B is a subset of A.
Yeah. So did we do it? We let X be in B, and we've concluded that X is in A.
Yeah,
Yeah, that works.
we did it.
We did it. All right. So when let X be in B and get X. So when X is in B, now it's required to show that X is in A. So sometimes, like when you've done what the requirement is, you can write. You don't have to. It's kind of a nice style to write as required at the end, and here's your little emoji. So there's a direct proof. Very nice. Let's do proof by contradiction. Proof by contradiction. So in a proof by contradiction, you assume the implication is false. Okay, so we're going to assume that implication is false. Specifically, that means what? The hypothesis is true, and
Conclusion is false.
okay, so we want to assume this is true, and that's false. Hypothesis true, conclusion is false. So what you write is this. In some format, you write something like the following. So, by way of contradiction, assume that A minus B union B is equal to A, and B is not a subset of A. You must write by way of contradiction. If you're doing a proof by contradiction, you must say so. Okay? If you're doing a direct proof, you must say so. You must tip off your reader. How do you tip off your reader? You say, assume the hypothesis is true. If you're doing a proof by contradiction, you must tip off your reader. You do that by saying by way of contradiction. All right, so by way of contradiction, here's our assumptions. So we're going to argue towards a contradiction. Okay, so proofs by contradiction are sometimes easier because, you know, there's something going on in a proof by contradiction that you kind of don't have otherwise. You know, you have more information, right? You're only assuming one thing in a direct proof. You assume the hypothesis is true, and that's it. You work from there. Here you're assuming two things. The hypothesis is true and the conclusion is false. So you kind of got more stuff to work with. Although what you're aiming for is not as clear. So sometimes proofs by contradiction are easier. Sometimes, actually, some things can only really be done by contradiction. There are some who like to quibble about that and say, well, you know, direct proofs are better than proofs by contradiction. And they may be simpler. From a logic standpoint, they're no better, however. All right, so since B is not a subset of A, there must be what? So B is not a subset of A. What does it mean for, you know, B to be a subset of A? X, an element of B, implies X is an element of A. So in order for for B to not be a subset of A, you got to have what?
The hypothesis to be true and the conclusion false.
Right, so specifically that is what?
X is an element of B, but not an element of A.
Yeah, there must be some X in B for which X is not an element of A. There's something in B that's not in A. Right? Well, because X is an element of B, so just like we did before, X is also an element of this union, A minus B union B. Come on. All right, because X is an element of B, all right, we must now have X is an element of whatever union B. But, right, A minus B union B is equal to A.
Equal to A,
Yeah.
which means X is an A.
Right, well,
That contradicts.
that's the contradiction right there. We assumed X is not in A, and now we get that X is in A. It can't be both. So once you get that, you write a contradiction. Which is a contradiction, achieving a contradiction, blah, 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 end of proof. In Latin, they say RAA, which I'm not even going to try to say it in Latin. Not that it's that hard, I just don't want to butcher it. Reduced to absurdity. So reduction to absurdity. So the absurdity is you know, that X is not in A and X is in A. Now, this is directly contradicting our assumption. It's not always that. You may contradict other things. Okay, other than your actual assumption. Typically, that's what it is. But these are shorter proofs, so it often comes out that you're just contradicting your assumption. If that's the case, then probably a direct proof would have worked. If you're just directly contradicting, well, no, actually the assumption is this. No, this is okay. This is okay. So We had a direct proof and proof by contradiction. Let's do proof by contrapositive. Proof by contrapositive. So contrapositive is right here. So you're trying to assume, you're trying to show R implies S is true. So in contrapositive, you assume S is false, show that R is then forced to be false. Again, the only time an implication is true or is false is when the hypothesis is true and the conclusion is false. So you assume R is true, show S is forced to be true. Or, contrapositively, assume S is false, show R is forced to be false. So let's do that. So you could say via contrapositive, but you just assume that your conclusion is false. Assume that B is not a subset of A. For a direct proof, you write just, assume your hypothesis is true. Here you just write assume the conclusion is false. By way of contradiction, you should say so, by way of contradiction. Some people say via contrapositive or by way of contrapositive. That's really not necessary. So just assume that B is not a subset of A. So just like before, therefore, there is some X in B. Well, there is some element X, let's write it a little differently, such that X is an element of B and X is not an element of A. Right? So following this same reasoning here, because X is an element of B, we get that X is an element of whatever union B. And then because right, now what? A little different. Right, because X is an element of B, we get that X is an element of A minus B union B. Right. However, now, since X is not in A, what? So X is in here, but X is not in A. So what's the case? What must be the case? A minus X is in. Sorry, I'm sorry. Go ahead. What were you going to say?
Oh, I was going to say that we could assume then that A minus B union B does not equal A.
Yeah, not assume, it isn't. A minus B union B is not equal to A. Well, you don't really need to say this, but let me put it. We get that A minus B union B is not equal to A, right? Because the element X is here, right? The element X is here, but the element X is not here. So they can't be the same sets. The same sets would have the same elements. Right? But this set has some that this set doesn't have, as required. Or not. End of proof emoji. So think about what emoji you like. I mean, what emoji says you?
Can we use it on the assignment?
Absolutely. So,
I might do my signature.
There you go. That's nice. That would be nice. So I submitted this paper for publication. It was a long time ago. And I used a different emoji than this. And the referee, the peer reviewer said, I don't know why he's using this weird symbol at the end of his proofs. So I changed it. It's anonymous referees, so I couldn't, somebody was intent on spoiling my fun. I mean, it wasn't like a super crazy thing that I was using, but. So this one is somewhat traditional. This is the most traditional. It could be black. It could be just like in typeface, just a clear little square. This is somewhat traditional. It's been used. In the past, like from the 60s back, they didn't put these end of proof emojis. And it made the paper much less readable. Adding those in made things much more readable. Because essentially when you're reading mathematics, you kind of want to skip over the proofs sometimes and get the story. Here's the story, now let's go back and do the proofs. But you can't skip over the proofs if you don't have these separators. Anyway, so let's do another example. So let A, B, and C be sets. I prove the following statement is true. Make sure I don't do the same mistake I did last time. Yeah, that's a different one. If A intersection C is the empty set, then B minus A union C is equal to B union C minus, B union C minus A. Now, in general, this is not the case. These two things are not equal. We're assuming that A intersection C is the empty set. Okay, so let's show this. So note. So it is not always true that B minus A union C is B union C minus A. How do I display this fact to you, that it's not always true? It's not always true that horses are brown. How do we do it? Show you the horse of a different color. So the horse of a different color, in mathematical terms, is called a counterexample. A counterexample. So it is not always true that this set and this set are equal. In order to do so, display that to you, we must give you the counterexample. With your counterexample, the cheesier, the simpler, the more absurd the example is, the better. Okay? When a statement is false, you want to show it fails, in a wide variety of cases. In particular, it fails in like the most trivial cases. Okay? So the cheesier, the better. So if you really want to be annoying when you talk to people, and people say, "Well, everybody loves chocolate," and you can just pop off and say, well, "I don't." That's the counterexample, right? And then they have to backtrack. If they're honest people, they'll have to backtrack and say something else. Well, most people do. What do you mean most? You got a percentage or something like that. Anyway, so it is not always true. So I have to give you a counterexample. For example, I mean, what are we trying to prove here? If A intersection C is the empty set, then that's the case. So, like, let's do an example in which A intersection C is not empty. So we'll say let A be equal to 1, 2. I think pretty much anything will work. B be equal to 1, 3. And C be equal to 2, 3. Then B minus A union C is equal to what? Well, what's B minus A? What's B minus A? There's B, there's A. So what's B minus A? Come on, guys. There's B.
3.
Just 3. Right? Union C. C is 2,
2, 3.
Yeah. So that's equal to the set 2, 3.
2, 3.
All right. And then B union C minus A. Well, what's B union C? There's B, there's C.
One, two, 3.
1, 2, 3 minus A, which is 1, 2, which is just equal to 3, right? And these are not the same. They're not equal. Okay, we're not showing that that's always true. We're just showing that if A intersection C is empty, then this is the case. All right. So let's do a direct proof. Let's do a couple direct proofs. What is the first sentence of my direct proof? We must assume the hypothesis is true, show that the conclusion is forced to be true. So what am I assuming is true?
A intersection C is not equal to the empty set.
Yeah, assume. Oh wait, I'm sorry. Oh boy. If A intersection C.
I'm looking at that.
I'm sorry. What did I know? I know. I did. What did I do? If A intersection C is the empty set. In this example, A intersection C is not the empty set, and you see that. This doesn't work out. Sorry. So assume that the hypothesis is true. A intersection C is the empty set. What do we need to show is true? Now, subject to that assumption, what do we need to prove is true? What do we need to show that is true subject to this assumption? What are we trying to prove? You assume the hypothesis is true. Show that. So assuming that A intersection C is empty. Now we want to show that what? Show that what?
B minus A union C equals B union C minus A.
Sure. How would we do that? Well, we have a couple different methods for showing that two sets are equal. Right? What's one method? What's the long method?
Show that they're contained in each other.
Yeah. Show that this is a subset of that. First is a subset of the second, and second is a subset of the first. Or, use those set identities. I mean, not that that'll necessarily work out, right? But, it would be shorter if it did. So let's do it that way. So now, B minus A union C is equal to. Okay, so by definition, B minus A is equal to what? What's B minus A by definition? Say it in terms of intersections and complements. It's B
Intersection A complement.
Yeah, B intersection A complement, union C. Right, which is equal to, by a distribution, B intersection C union A complement intersection C. Or wait. A complement union B minus A union C. That's B intersection A complement union C. So that's B union C intersection A complement union C. Unfortunately, these won't work out. I thought it would.
We might have to do it the long way.
Yeah, we have to do it the long way because we don't have because this is empty set. Because this is the empty set, is there some way I can fix that? A naught intersection C. I don't think so. Let's see, maybe if we go the other way, B union C. So this is B union C intersection A naught. So it's C intersection A naught union B intersection A naught. Yeah, unfortunately. Okay. So let this be true. Okay, so first we want to show that B minus A union C is a subset of B union C minus A. Okay, we're assuming this is true. Now you want to show that this is true. So we're going to do it by showing the first is a subset of the second, and the second is a subset of the first. So we'll start with this one. So let X be an element of B minus A union C. By definition, right, X is an element of B minus A, or X is an element of C. So by definition, X is in B minus A, or X is in C. Okay? So first, consider the case so if X is an element of B minus A,
We have that
mhm,
X is an element of B and X is not an element of A.
X is an element of B and X is not an element of A. Because X is an element of B, X is an element of B union C also. All right. X is an element of B union C as well. Remember the definition of union. Union means you're in, X is in B or X is in C. Right? I already know X is in B. So X is in B or C. I'm adding in some information that may seem irrelevant, but it's not really. Right? I mean, I live in Ohio. Right? Daniel Slavati, he lives in Ohio. Therefore, Daniel Slavati either lives in Ohio or Kentucky. That's true as well. Even though what Kentucky has to do with it, well, nothing really. Okay, it is a true statement. Okay, so X is in B union C, and X is not in A. Which means what? We have that X is in B union C, and X is not in A. Therefore, what? I have X in
X is in B union C minus A.
Yeah. Right? This means X is in B union C, and X is not in A. I have both of those facts. I got X is not in A, and I've got X is in B union C. I obtained the fact that X is in B union C via the known fact that X was in B. All right, that's half of that part. Right? Let X be an element of B union C minus A. So by definition, X is in B minus A, or X is in C. If X is in B minus A, then X is in B union C minus A. All right? So now, if X is in C, right, whenever you have an either or, it splits your proof into two cases, typically. Right, we're almost out of time. Well, we are out of time here. So we'll finish this one next time, okay? Yeah, we'll finish this proof next time, okay? So we'll see you on Friday. Please take a look at the one we just did already. Give that one a go yourself. Look at the proofs from last time and give those a go yourself, okay? That's the practice that you need, in order to get up to speed on the material, okay? You need to go over the examples on your own. Okay, have a good day, everybody.